In this video, we're going to discuss an application of binary search trees, and that is to use a binary search tree to implement the list interface, giving us an ordered list that has much better efficiency than the array-based ordered list we saw previously. So just as a reminder, we have this list interface that has some methods to remove the first or last element, to return what that first or last element is, remove a specific element, and check to see if an element is contained in the list. And then we have methods to check if it's empty, the size of that, and then we can also get an iterator that will allow us to iterate over the elements of the list. Now, an ordered list actually keeps the elements of the list in order, so it adds another method add, and when we add to an ordered list, that element that we add goes in its proper place. So if we start off with a jumbled bunch of elements, then we can add those to an ordered list one by one. So the first element we add is 12, but then when we add 7, notice it goes before the 12. The next thing is 1. When we add 1, it's going to be first. 4 will go between the 1 and the 7. 18 will go at the end. 10 will go in between 7 and 12. 20 goes at the end. And then 9 goes between 7 and 10. So as we're adding to that ordered list, everything goes in its proper place. A search tree also adds elements in their proper place to maintain an order. So let's move these elements to the sides to get them out of the way to build our tree, and we'll add the elements to a search tree in the same order that we added them to the ordered list. So we add 12 first, so it'll be our root. 7's next, it'll go in the left subtree of 12. 1 is next, left subtree of 12, left subtree of 7. 4 is next, so that's going to be in the left subtree of 12 and 7, but since 4 is greater than 1, it'll go in the right subtree of 1. 18 will go in the right subtree because it's greater than 12. 10 is less than 12, so it goes in the left subtree, and then it goes in the right subtree of 7 because it's greater than 7. 9 is less than 12, greater than 7, but less than 10, so it goes in the right subtree of 10. And 20 is larger than 12, it's larger than 18, so it goes in the right subtree of 12 and 18. So both an ordered list and a search tree maintain their elements in order. Now the client who's using an ordered list doesn't really care what that structure is. They're just interacting with the list through the methods in the interface. So for an ordered list, we have the ordered list interface, which extends the list interface. So we have access to all of these methods, and that's what the user is going to interact with. So the elements could be stored in random order as far as the user cares. It's just that when they call first, they want to get 1 out. When they call last, they want to get 20 out. If they add 30, they want that to be what gets returned when they call last. When they get an iterator, they expect all of the elements of the ordered list to be in that iterator in their correct order. But that underlying data structure doesn't really matter, except for efficiency. So here's our list interface. Here's our binary search tree interface, which extends binary tree. Now, I did take some of the methods out so that everything would fit on one screen here, but notice the similarities. They both have a method that will remove the smallest element. Remove first in a list is the same as remove min in the binary search tree. We will still remove the smallest element. Remove last or remove max both remove the largest element. Remove and remove element both remove a specific element. First and last and find min and find max return the smallest or largest elements in the data structure. Contains, they both have a method to return whether or not a specific element is in the data structure. They have methods to determine is the data structure empty and what its size is, and they both return an iterator. Our binary search tree iterator, remember, returns things in order. So there's no difference if you add a bunch of elements to an ordered list, you add a bunch of elements to a binary search tree, the iterator that gets returned is going to be the same if the elements you added to both structures are the same. And they both have a toString, and most importantly of all, they both have a method to add something to the data structure that will put that element in its correct order relative to other elements that already exist in the data structure. So we can create a class called BinaryTreeList that will implement the list interface and the ordered list interface. It'll also implement iterable so that we're able to iterate over the elements that are there. Now, the user doesn't really care that there's a tree or a list or whatever. They just know that there's some data structure that implements the ordered list interface, and that's how the client is going to interact with the data structure. So when the client calls first, it's going to return the smallest element in the structure, which is a 1. We can call findMin on this binary search tree to get that value. We can call findMax. When the client calls last, that's the largest element, so we can call findMax on the binary search tree to return that to the user. And then finally, the iterator is going to return all the elements in the structure in sorted order. Well, a binary search tree iterator does that. So again, we're using the binary search tree methods to implement the ordered list interface. And that gives us some advantages. If you're working at the beginning of the ordered list, maybe you don't get those efficiency advantages. But the big advantage you get here is that when you're adding and removing to this list, it's much more efficient than adding to an ordered list. Traversing takes the same amount of time, but there is, however, a little bit of a performance penalty for findMin and findMax because in an array-based implementation, you have direct access to the first and last elements. So by implementing a binary search tree list, that gives the user the option of when they need an ordered list, they can decide, do they want to trade off more efficiency for adding and removing to losing a little efficiency when they look for the smallest and largest elements in the collection. Now, for things like traversing, those are both linear time for both data structures, and so there's not really any difference there. But again, the idea here is to give the client more options as far as the performance characteristics of the collection that they're going to use. And again, remember, if they program to the interface and later on they decide they want a different collection, then they can swap that out very easily with a minimal impact to their code. So let's take a look at what this looks like in our code. So here we have the binary search tree that implements the list, ordered list, and iterable interfaces. We're going to have a private data member tree because, again, we don't want to provide the tree methods here. We only want to provide the list methods. So our constructor is going to create a new binary search tree. And then for each method in the list interface, we're going to call the corresponding method in the binary search tree class. So our add method will call the binary search tree add element method with the same parameter. Remove first and remove last, call remove min or remove max in our binary search tree. For the remove method in the list interface, we call the remove element method of the tree class. For first and last, we call find min and find max. And then for our iterator, we return an in order iterator. Now remember, our tree interface actually has a lot of different iterators, and we want to make sure we return the in order iterator explicitly so that the items are returned in order. We wouldn't want to use a binary search tree to implement an ordered list and then return things in level order or pre-order. Since it's a binary search tree, we want to do it in order because an in-order traversal of a binary search tree yields the elements in order. And then finally, contains is empty in size, we simply return the binary search tree method. So again, by using the methods of the binary search tree, we can implement the ordered list interface, giving the user additional options to decide what sort of performance trade-offs they want to make based on what they're trying to do with their list. So I've taken the list examples driver class we had back in module 6, and I took out the unordered list because that's not interesting. And you'll notice now I'm getting an error because it doesn't know what an array ordered list is because we haven't defined one of those in this module. However, I'll change this to a binary search tree list, and we're not going to initialize it with a size. So now, notice I didn't have to change any of the code other than my constructor call. And when I run this, you'll see that my iterator returns the items in order. As many times as I run that, it'll give me the elements of this data structure in order. I can call the other list methods with no issue. And so now, whether I want the performance characteristics of a binary search tree or a list, it's up to me as the client to decide which of those implementations I want to use that best fits what I'm trying to accomplish with this code.